video is to take the standard form differential equation we calculated in the last video and use MATLAB to calculate the solution using Euler's method. So just to recap, this was the differential equation we were given, and these are the boundary conditions. That is the domain of interest. We are going to use Euler's method. In other words, if we know in standard form the variables are t and z, so if we know t and z at x equals 0, we can then use this to calculate the first derivatives, dt dx and dz dx, and then use the first derivative to extrapolate what t and z would be at some x delta x away. And we did this for one step using a delta x of 0.1. So now we need to code it. So I'm going to start by writing a function that defines the differential equation. Let's put the differential equation on the screen. New function. Okay, I'm going to call this differential equation. And the standard form requires that we give it an independent variable, which we're going to call x. It's usually x or t. And then we're going to give it some vector y. The output is going to be y prime given numerical input values for x and y. So I like to unpack y. T, I like to think of, so y is a vector of t and z, but I don't want to have to worry about that. So I'm going to say t is y of 1 and z is y of 2. I don't think you need the comma 1 there, but I'm going to put it there just in case. Y would be a column vector. And now y prime is going to be z and then t plus x minus t times z. Okay, let's save that. Let's make a new script. And I'm going to say my y initial was given in the problem, and that was 10, 1. So let's just do one step. Or first let's calculate y prime 0. So x was 0 and y 0. Let's run that. I'm going to call this okay, let's see if we can. So y prime 0 is 1, 0. That is what we calculated. So if I wanted to calculate y prime at delta x equals 0.1, I actually don't really need this, but I'll just calculate it just to, so you can see it. If I say delta x is 0.1, doing one step of Euler's method should get us the number that we predicted here, 10.1 and 1. That's correct. Now we're not just interested in a single step, we're actually interested in taking several steps to go from, I'm going to go from 0 to 10, and then I'm going to run Euler's method again to go from 0 to negative 10. So let's just say y series, positive, let's say 0 to 10. How about this? I'm going to say x 0 to 10 comma y 0 to 10 equals Euler's method. I have to write this function. Okay, what do I need to send? I need to send it the differential equation. I need to tell it the x range. I'm going to say 0 to 10. I'm going to need a initial value for y, and I'm going to need to tell it a step size. I'll say 0.1. So that should be enough to get us started. Of course, we can't run it until we define the function. So I'm going to make a new function. I want to call it Euler's method, so let's copy that. Euler's method. Let's see, what did I send to it? I don't have to name these the same. So I'm going to call this y prime. I'm going to call this x range. I'll keep that as y0 and I'll call that h for the step size. And the output is going to be x range, x solution, and then y solution. And I'm going to need to apply Euler's method over and over again. So I'm going to say x solution is going to be an array that's going to start at x range of 1. It's going to take steps of h, and it's going to end at x range of 2. And now y is going to have the same number of columns, but the number of rows depends on the equation. So in this case, there's 2 equations, but we actually don't know the number of equations necessarily. It can be any number. So I'm going to look at the dimensions of y0 to get the number of equations. I'm trying to write a function that will work regardless of how many equations it's sent. Okay, so that's the number of equations. So now y solution, I'm going to declare it as zeros. Zeros, the number of rows is going to be the number of equations. And then I'm going to use the number of columns should be the number of x values. So now I'm going to initiate y solution. The first column is going to equal y0. And now I'm going to say for I equals 2 colon length x solution, I'm going to fill in the rest of the y values. So for every I, it's going to equal y solution I minus 1 plus h, the step size, times y prime. Now y prime is going to depend on the x value in the previous column and also the previous y values. I've got a warning here which suggests that I have too many parentheses. Okay, let's try that. Save it as Euler's method, and let's see if our script runs. Okay, something happened. So you can see with the step size of 0.1, that's the first step. Now it continues. Okay, that's promising. So let's now go backwards. I don't want to say, I'll put a minus sign in a variable name. So it's all going to be the same inputs, except now I'm going to go from 0 to -10, and I'm going to use a negative step size. Let's actually, let's say step size equals 0.1. In case I want to change it, okay, let's see if that runs. I'm going to take the semicolon off of that just to see. Yeah, something happened. So now let's put our X series together. So I'm going to need to reverse the 0 to -10. I'm going to go from the end, which should be -10, colon, -1, colon 2. I don't want the first point because that's 0, and the 0 is also in the list that goes forward. So now I'm going to say x 0 to 10, and that is already in the right order. So let's run that and see if my x series is correct. So the x series starts at -10, it goes to 0, and then I don't see a repeated 0. That's good. Looks like it worked right. And now I can put together the y series. So now it's going to be y 0 to -10, all the rows and those columns, and then I think that'll work. Let's go ahead and plot the solution. It did not like that. Because I put an O instead of a 0 there. Okay, actually I did not intend to plot, so it actually plotted two things. This I think is t, and this is actually t prime. It looks reasonable, but I actually didn't intend to plot. Let's actually do this. Let's call this t series. And I don't actually need both rows, I just need the first row. Remember that z was a variable that we invented so that we could put the equation in standard form. So the solution to this is really just t as a function of z. So let's go ahead and I did something else wrong. Y series. Line 13. Oops. I changed it to t series. Okay, now this may not be accurate. It's unclear to me, actually. So let's, what I want to do here is I'm going to run this twice for different step sizes. And I'm going to call this T series A and X series A and going to do a step size that's 10 times smaller than that. And I'm going to call this 2 and 2. And I'm going to plot the two calculations on the same axis. And if my step size was small enough, then I would expect that those two curves would overlap. So clearly they don't overlap. They look kind of similar though. So let's go even further. So if I say that's 0.01 and that's 0.001. Okay, so now they overlap. If you zoom in enough, I don't think it's perfect, but it should give you an idea of what a reasonable step size ought to be. I don't feel like going any smaller, and I think we have accomplished our mission.